Okay, hi. This is the first video for structure and properties of matter. I've been a bit confused as to how to organize these videos. I feel like the main thing that's super important is the homework. This is just going to be a quick theory video. I'm going to be doing a couple of lessons at the same time just because mostly what's important is that you know how to do the questions. You do need a bit of background, but hopefully if you've come to class and paid a smidgen of attention, you would know relatively what's going on here. So we're just gonna skip all this bit because we don't really need to know it. It's good to know that Thomson first came up with the chocolate chip pudding or blueberry pudding or whatever you want to call it model, where he thought that the nucleus was not the nucleus, the atom as a whole was just a positively charged sphere, and there were electrons that were embedded like chocolate chips in a muffin, right? That was his idea. And so Rutherford set out to test that using the gold foil experiment. So it's important to know the gold foil experiment. You have to explain a hypothesis. So the hypothesis was that all the alpha particles, so again, alpha particles is a helium nucleus, so a particle with two protons and two neutrons. Obviously, at this point, nobody knew what the nucleus was. This was the point of this experiment, was to discover the nucleus, or to prove that its existence was prove that it exists. So at this point, all they knew about alpha particles was it was the one of the products of radioactive decay. So when you had some kind of uranium, it radioactively decayed into alpha particles and lead, and that was it was known that it was radioactive using Marie Curie's work and Becquerel's work, and therefore it was known that it was positively charged, but nothing much was. They didn't know it was a helium nucleus per se. But okay, alpha particles, two protons, two neutrons, right? They are going to throw alpha particles, and based on Thomson's model, what should have happened is all the alpha particles should have passed straight through, because there was no concentrated region of positive charge to kind of repel or deflect these alpha particles. They expected to just pass straight through the atoms. So what was the experiment that they did? That's exactly what they did, right? They had a tiny little gap where alpha particles would come through. So these were the alpha particles, and it struck a thin gold foil. So a super thin, nanometer thin gold foil made up of a couple of atoms thick. So it was very thin, gold leaf, and they shone alpha particles or bombarded this gold foil with alpha particles. Right? So step 1, radioactive sample emits alpha particles. Step 2, beam of alpha particles hits gold foil. And step 3 was these alpha particles then deflected or passed straight through. So you expected all the flashes to be occurring somewhere over here because the alpha particles were passing straight through. But what happened was there was some minor deflections, which was not accepted, or which was not expected. There were some major deflections, and 1 in a million, the alpha particle bounced right back. They actually had to extend this detector. There's a lot of funny stories about why they decided to do that and how long they had to spend in order to get these results. But they did spend a long time, and they finally got a result. I should probably use a different colored pen. As you can see, they finally got extended this kind of detector and figured out that 1 in a million alpha particles bounced right back. And so these were the conclusions that they had. They observed some particle had minor deflections, some had major deflections, and some just bounced right back. Right? And this was the conclusion that they came to. I don't actually have a conclusion side, but the conclusion that they came to was that the atom has a very densely positively charged center called the nucleus, and that was very small, and most of the atom is just empty space. The electrons circled around the nucleus like planets circled around the sun. So at this point, Newton's models of physics were very dominant. People were learning about them, so they're like, oh yeah, electrons should circle around the nucleus just like planets circle around the sun. There is a catch, however. The limits of the Rutherford model here is based on that theory, the electrons should experience acceleration of all times. So any charged particle that is accelerating must be emitting energy. So that was a known rule at the time. And for these electrons, we know electrons charged, and the hypothesis was, okay, electrons are circling around the nucleus, but they're not emitting any energy, because otherwise they would just collapse into the nucleus. They would just lose their energy slowly and slowly, and then their kinetic energy would be zero, and the electrons would basically stop and crashed into the nucleus. And that's obviously does not occur. There must be a different model of the atom. So something has to be added. So the limit of the Rutherford model is that he did not explain how charged particles could orbit the nucleus without losing energy. Then comes the hydrogen, or emission spectrum of hydrogen, where they had hydrogen show distinct lines in the spectrum. So this is a visible spectrum, and the lines basically show photons that are being released at a particular energy. So Bohr came up with this idea that electrons do not exist in any region of space. They have to exist in some orbits with specific energy levels, right? So this is where our nucleus is, with its protons and neutrons, and then we have our shells, n equals 1, n equals 2, n equals 3 shells. This is Bohr's idea. Again, this is what we studied in grade 9. There's like 2 electrons in the first shell, there's 8 in the second shell, 8 in the third shell. And what he used to explain this was the hydrogen spectrum. So he said, when an electron gets energy, so let's say this is shell 1, this is shell 2, so these shells are quantized, so they have fixed they're multiples of a fixed number of energy, right? So here the first shell had some kind of energy, the second shell had a fixed energy that was quantized, and so therefore there could be no kind of 1.5 shell. There was no such shell that existed. The shells had to be quantized, as in they had to be whole number multiples of some fixed constant, right? So we keep going up from 1, 2, 3, 4, 5, 6, and there's infinity number of shells according to Bohr. And again, what he explained was the hydrogen spectrum, or emission spectrum of hydrogen. When an electron dropped down from the third shell to the second shell, this again, as you get closer and closer to the nucleus, there's less energy, so that it's becoming more and more stable. So the second shell has a lower energy than third shell. So when you drop down, you release energy. So that photon that's released shows up as this line. If you drop from the fourth shell to the second shell, the photon, that's more energy drop. So it's a shifted to the blue length because it's higher energy. But there's a released a photon of a specific wavelength. Again, this explains why you don't have a line over here, because this energy difference would correspond to, let's say, 2.5 to 2, or 3.5 to 2, which cannot happen because there's no electron in the 3.5 shell. There's only 1, 2, 3, 4 set number of drops that can occur, either 3 to 2, or 4 to 2, or 5 to 2, or 6 to 2, and therefore you have only 4 lines in the hydrogen spectrum. And this was corroborated by the hydrogen spectrum evidence, so this was where quantization theory was coming up a lot, so Bohr suggested this theory. But officially, the atom has specific allowable energy levels, and the energy levels, as in he's called these orbits. So the electron circles around the orbits. So while one of its stationary states, atoms do not emit energy. Again, you don't really have to worry about why the atom does not emit energy, just that it doesn't when it's in this shell, because it's stable in that shell, right? Limitations. Hydrogen was easily explained. There's only 4 lines, but if you look at neon, if you look at a emission spectrum of neon, there's a bunch of other lines here, which make this very confusing. So you're wondering, okay, where do all these other lines come from? It looks like you don't have like your set 4 to 2, 3 to 2, 5 to 2, 6 to 2. You have other bunch of things that are going on, which is a problem. Bohr didn't really explain that. And so came along quantum theory. Again, you don't really have to know any of this. This is actually This diagram is a simpler version to explain the uncertainty principle. It's actually relatively, I won't say inaccurate, but it is a common misconception. It's just a thought experiment to kind of understand the uncertainty principle, but realistically, the uncertainty principle does not work this way. It is a fundamental property of the universe and not our limitations on measuring stuff. But again, none of this technically matters. So we're going to move on into our orbitals. So what quantization basically decided is, okay, now electrons are not circling around the nucleus in orbits. That's no longer a thing. Now because electron is a wave, so now, up till now, you've been kind of thinking of this electron as this tiny particle that's like roaming around the nucleus. But now we have to think of an electron as a wave. Okay, so what does a wave look like? It looks like this. You've all hopefully done some sort of math functions or some kind of math course where you've looked at a sine wave. And if I ask you to tell me the position of this wave, it's impossible for you to tell me the position of this wave. This wave exists infinitely in space. The wave keeps going on both directions endlessly. There's no start or finish to a sine wave. So a wave's position in space is kind of everywhere, right? And that's the problem. Because electrons have significant wave nature, so they're kind of like a particle, but mostly also exhibit a large amount of wave properties. You can't say that the electron is here, right? It's not like the electron is exactly at this point or in this circle. You can't say any of that because the electron is a wave. It exists everywhere at the same time. There are some, like, obviously the electron does not exist everywhere at the same time. You can kind of analyze based on electron's properties where the electron is most likely to be localized or most likely to be concentrated around, and we can call these like electron maps or electron density maps. And where the electron is most likely to be found is given by a region of space called the orbital. So orbital is no longer like an orbit where you have like a fixed shell where the electron's going around. It's literally a mathematical function that defines the space in which the electron is most likely to be found, right? So it's not a fixed container. It's not the electron is in here. It's just a function that describes a probability density function, right? So there are four different kinds of quantum numbers that give electron more shapes. So just like Bohr said, okay, we have shell number 1, shell number 2. Quantum numbers are not shells, but there are four different quantum numbers that tell you, okay, let's describe the function that represents the probability density of where this electron is found. So, long story short, all you need to know is that there are four quantum numbers. You have to know how to describe quantum numbers, and again, when we do practice, hopefully they'll be a lot clearer. So the first quantum number gives the size of the orbital and energy level, and this is called n, and it ranges from 1 to 7, mostly corresponding to, so I should have had that ready, but if we go to, again, this is a good resource, ptable.com, mostly corresponding to the 1 to 7 periods on the periodic table. Right, more or less corresponding to those. That is our first quantum number. Our second quantum number gives us the shape of the orbital. So orbitals can come in different shapes. We'll look at that in the next PowerPoint. But the shape of the orbital, the second quantum number is denoted L. So our first quantum number is n, ranges from 1 to 7. Our second quantum number is L. This ranges from 0 to n minus 1. So what does that mean, 0 to n minus 1? So for an n equals 1, because that's the lowest n number, our L can be 0. For n equals 2, our L can be 0, or it can be 1, because 2 minus 1 is 1. So that's the range of L. For n equals 3, L equals 0, or 1, or 2. N equals 4, and L equals 0, 1, 2, or 3. But we're not going to use 0, 1, 2, and 3. we are going to use SPDF. So basically, this L, instead of a 0, it's an S. So we have to remember S corresponds to 0, P corresponds to 1, D corresponds to 2, and F corresponds to 3. And these are just the letters that we assign a second quantum number of a certain number. So if second quantum number is 0, that means it's an S. 0 is S, 1 means P, S, P, D, S, P, D, F. Right? That's just what the second quantum. So if a second quantum number has a certain shape, you call it an S orbital. If it's a certain shape, you call it a p orbital. And we'll get to what those shapes look like in a bit. Okay, there we go. S orbitals are shaped like, so if the orbital is shaped like a sphere, it's an S orbital. We denote that L value of 0, but it's an S orbital. So you can say L equals S as well. Same thing. L being the symbol for the second quantum number. P orbitals are like dumbbell shaped. D orbitals are double dumbbell and donut shaped. Again, you don't have to know the shapes, just know that the different kinds of shapes that correspond to the orbitals. That's why you have SPD orbitals, because they have different shapes. The third quantum number is the magnetic quantum number, and this is also represented in the diagram. So here, this is just this is n equals 1, n equals 2, n equals 3. So this is a 1s orbital, this is a 2s orbital, this is a 3s orbital. Here, all of these, you'll notice, have the same n and l values. This is all 2p, 2p, 2p. They're just oriented along different. So this is along the z-axis, this is along the y-axis, this is along the x-axis. So these are called degenerate orbitals. They have equal energy, and they are given by the third quantum number. So the degenerate orbital gives the orientation, which axis is it going along. It's denoted by ml, and you have, it ranges from negative L to 0 to positive L for every L. So for example, the s orbital will range from negative 0 to 0 to 0, which is just 0, so there's only one ml value. The p orbital, L equals 1, so this ranges from negative 1 to 0 to 1, which means there's 3 of them. And that's why we see 3 p orbitals here. This denotes negative 1, 0, and 1. Right? The d orbital, again, ranges from negative 2 to negative 1, 0, 1, 2. So there's 5 of them. That's why we see 5 different shapes for the d orbital. Negative 2, negative 1, 0, 1, 2, corresponding to 5 different ml, or magnetic spin quantum number values. And F orbital, having 3, ranges from negative 3, negative 2, negative 1, 0, 1, 2, 3. So there's 7 of them. The shape of the F orbital, you don't really have to, it's, I think, on the next PowerPoint, you don't really have to know that. The last quantum number of an electron denotes its spin. So you can have a positive spin, which is denoted by an up arrow or an up half arrow, or a negative spin, which is denoted by a down arrow or a down half arrow. Doesn't really matter. If you put the full arrow in, I'm used to putting the half arrows in, so I'll be drawing it like this, but you can put the full arrow, no problem. Okay, and that was more or less what we did about a brief understanding. So basically, again, I think I have, okay, we'll get back to electronic configurations, but what you need to know basically is the gold foil experiment, what Bohr said, the limitations of Bohr's theory, because it couldn't explain the emission spectrum of gases other than hydrogen, so neon and helium, it couldn't explain those, and so we had to bring in quantum theory. The only thing you need to know about quantum theory is that it has now 4 quantum numbers that describe where the electron is now. So again, principal quantum number ranges from 1 to 7. Secondary quantum number ranges from 0 to n minus 1. And we use SPDF to denote 0 to whatever secondary quantum number. So 0 would be, secondary quantum number 0 corresponds to S. Secondary quantum number 1 corresponds to P, etc. We talked about the magnetic quantum number, and these are what the F double donuts and other weird things is what the F orbital looks like. There are 7 of them, as we talked about. But yeah. So each this is another important rule, each orientation of the orbital, so each of these guys can hold a maximum of 2 electrons, one with positive spin, one with negative spin. So each orbital, so the p orbital, since it has 3 subshells or suborbitals, can hold a maximum of 6 electrons. 6 electrons maximum. And why does it do that? Because this can hold 2, this holds 2, this holds 2, so that's 6. The d orbital can hold a maximum of 10 electrons, because each of these suborbitals can hold 2, and there's 5 of them in the d, so 10 electron max. The s orbital has only 1 suborbital, so it's a 2 electron max. The f orbital would be a 14 electron max, because again, each suborbital can hold 2 electrons, and there are 7 suborbitals in the f. -3, -2, -1, 0, 1, 2, 3. That's 7. Okay, we're going to, I think, in a new video, learn about how to assign orbitals to electrons, and then we'll move on to the next half of the theory and stuff. Alright, so see everybody in class. Whoops.